All right. We also have the sum of a finite geometric sequence. So we have kind of like a formula to help us find the sum of a finite geometric sequence. Again, we use this symbol where if we start at 1 and we go to whatever term we're looking for, our base formula looks something like this. We're going to take our first term and we're going to multiply it by 1 minus r to the nth term over 1 minus r. So again, make sure you have this written down. This is how you find the sum of an infinite geometric sequence. So looking at an example, let's say I'm looking for the sum of the first 12 terms of the sequence is 4 times 0.3 to the nth power. So again, if you just wrote it out, it would be something like 4 so it'd be 4 times 0.3 to the first, plus 4 times 0.3 to the second, plus 4 times 0.3 to the third. And then we would end with 4 times 0.3 to the 12th power. So if we use our formula that we kind of just figured out, we were going to say, all right, I'm going to take my first term, which is 4 times 0.3, and I'm going to multiply that by 1 minus 0.3 to the 12th power, all over 1 minus 0.3. And once I go through, simplify that, again, following order of operations, I'm going to get an answer of approximately 1.714. So the sum of the first 12 terms of 4 times 0.3 to the nth power is about 1.714. Now, if I were to change, now notice again, this was n equals 1. If I changed it to n equals 0, really what I'm doing is I'm just adding one more term. So if I think about what is 4 times 0.3 to the 0 power, that's like 4, anything to the power of 0 is 1, it's 4. So I could just take my previous answer and add this one additional term, which gives me 5.714. So again, the difference is that we started at 0 rather than starting at 1. We also have infinite geometric series, which again go on for forever. So if we were trying to find the sum of an infinite geometric series, I equals 0, going all the way to infinity, whatever our term is, a sub 1 over 1 minus r. Now note, if the absolute value of r is greater than or equal to 1, it does not have a sum. So if we take the example of, all right, I'm going to take the first term, go all the way to the infinity. I'm going to use this equation. Oops. I'm going to say this is n minus 1. We would say, okay, using my equation that we just found right here, we are going to plug in, and again, this is 4 times 4 to the first power, 4 to the second power, 4 to the third power, 4 to the fourth power, moving on and on and on. So if we use this formula, we're going to get my first term, which is, again, if I plug in a 1, is 4 times 0.6. 1 minus 1 is 0. And we just said anything to the 0 power is 1. So 4 times 1 is 4. So my first term is a 4 over 1 minus, my rate is 0.6. So 1 minus 0.6 is 0.4. So 4 divided by 0.4 equals 10. If we have a series, an infinite geometric series, so maybe the question says find the sum of 3 plus 0.3 plus 0.03 plus 0.003 plus all the way to infinity. Again, we got to figure out our first term. Our first term is 3. Now we got to figure out the common ratio. So I could take, again, 0.3 divided by 3, 0.03 divided by 3. And when I do that, I should get an answer of 0.01. So when I plug those into my formula, a sub 1, again, what do I need? A sub 1 is 3, so 3 over, So the sum equals 3 over 1 minus 0.01. So that's going to equal 3 over 0.99. And when you divide 3 by 0.99, you get oh, excuse me, I kind of goofed up here. So if we go back here, this should have been a 0.3. So 0.03 divided by 3 is it's 0.1. So I was off by a decimal point. So again, when I change that into my equation here, it's not going to be 0.99. It's going to just be 0.9, which is 3 1/3 or 3.3333333 repeating. Let's see here. Last example. It's about an annuity, an increase in annuity. So you deposit $50. On the first day of each month in a savings account that pays 6% compound interest monthly. First of the month. It's the first of the month. Bone Thugs and Harmony reference there. What is the balance at the end of 2 years? All right, so this is a type of savings plan that is called an increasing annuity. So as you get older and you start making more money, you might want to develop a savings plan that's something like this. So again, if it's monthly, after 2 years, there's 12 months in a year, 2 years, that means I'm looking for after 24 terms. So again, I'm increasing by 50, or my first term is 50. I'm increasing by 60% or 6%, which again, a percent as a decimal is going to be 0.06. So my rate is going to be 1 plus 0.06, and that's divided by the 12 months. And then 24 minus 1 is 23. So as I go through and start simplifying, I'm going to get 50. So this is 50 times 1.005 to the 23rd power. The last deposit will gain interest for only 1 month, and its balance will be a sub 1 over equals 50, 1 plus 0.06 over 12 to the first power is just 50 times 1.005. Again, to the first, you don't necessarily need that. So the total balance in the annuity will be the sum of the balance of the 24 deposits using our formula for the sum of a finite geometric series, with our first term being 50 times 1.005 and our rate being 1.005. We take the formula, let's see here, a sub 1 minus r to the n over 1 minus r. So when we plug this in, I want the 24th the sum of the first 24 terms, which is 2 years. I'm going to take 50. Again, my first term we just found is 50 times 1.005. And then I'm going to do 1 minus 1.005 to the 24th power all over 1 minus 1.005. And as I go through and simplify that, again, this is just punching into your calculator. We're going to get about $1,277.96. So not bad. If you put $50 into a bank account for 24 months at 6% compound interest, after 2 years, that's going to be $1,277.96.